So we're looking at proof by induction, but with divisibility this time. So first example I'm going to work through is prove by induction that for all positive integers n, 3 to the power of 2n plus 11 is divisible by 4. Okay, so it's going to have the same 4 steps as what we've done already. So the first step, and I'll bullet point it like we did last week, is when n equals 1. Okay, so we literally substitute n equals 1 in. This time though, we don't need to show that the left hand side equals the right hand side. We need to show that when n is 1, this will be divisible by 4. So we've got 3 to the power of 2 times 1 plus 11. So that's 3 squared is 9, add 11 equals 20. We can show it, so 20 divided by 4 equals 5. So true for n equals 1. Okay, so exactly the same steps. The next step is we assume it's true. So assume true for n equals k. And this is where it's going to slightly change here. So we're still going to do 3 to the power of 2k plus 11 is divisible by 4. Okay, but what we can do here now, and this is where it changes slightly compared to a series question from last week, is if we're saying that this is divisible by 4, we can put 3 to the, oh, that's supposed to be a 3, let me rewrite that, 3 to the power of 2k plus 11 equal to 4, and I'm going to use a, 4 times a letter, okay, where a is a positive integer. Okay, so hopefully that makes sense. If we're saying it's divisible by 4, it means it's equal to 4 times something. Yeah, where a is a positive integer. Okay, and therefore, because if you think in the moment we're going to have to let n equal k plus 1, we can actually rewrite this so we just get the term with a k in on one side. So we can write this as 3 to the power of 2k equals 4a minus 11, just so we've just got the part that we need with a k in. Okay, so the next bit we do then is when n equals k plus 1. Remember, we need to prove that it's true for this one, or show that it's true. So when n equals k plus 1, we can replace, coming back to our original one, we've got 3 to the power of 2 times k plus 1 plus 11. Okay, and then we can expand out this bracket, because remember what we need to try and show now is that this is going to be similar to this in some shape or form. Okay, so we've got 3 to the power of 2k plus 2 plus 11. Now, using rules of indices, we can rewrite this part. How? So we're not going to use logs, but if you just think about rules of indices, if I gave you something like, I don't know, x to the power of 4 times x to the power of 5, that would be written as x to the power of 9. Do you agree? Because we add the powers. Well, that's technically what we've got here, just the other way round. We've got a power of these two added together, means we can write it as 3 to the power of 2k times by 3 to the power of 2. Because we add those together then to give us that, wouldn't we? Add 11. Make sense? Okay, so that 3 squared is 9, so we've got 9 brackets 3 to the power of 2k, add 11, you agree? Well, 3 to the power of 2k, we've rewritten up here as 4a minus 11. That was in our second step. So we can substitute that in now, because if 3 to the power of 2k is equal to 4a minus 11, we can substitute that into here. So we've got 9 brackets 4a minus 11 plus 11. Expand out the brackets. Okay, so expanding out the brackets, we get 36a minus 99 plus 11, which is 36a minus 88. And hopefully you can see, remember we need to show this is divisible by 4. Well, hopefully you can see 4 is a factor of both of those. So we take the 4 outside to show that 4 goes in, giving us 9a minus 22 inside the bracket. So this is divisible by 4. So true for n equals k plus 1. And then we finish with our sentence like we do all the time. Okay, so if true for n equals k plus 1, if true for n equals k, then true for n equals k plus 1, as true for n equals 1, 3 to the power of 2n plus 11 is divisible by 4, divisible by 4 for all positive integers n.